if you remember, not last week, but the week before, we started talking about the layers. All right, the layers of the OSI model, and then the TCP/IP model. So if you remember, we looked at the physical layer last week. So if you remember, we sort of have the 7 layers of the OSI model, and we've been going from the bottom, physical layer, and that's the second one is the data link layer. And if you remember, I had a way of remembering it, but you don't have to use it. It's a bit silly because that doesn't make sense for you guys. Phil Donahue never televise sick people anymore. And that becomes the physical layer, data link layer, network layer, transport layer, session layer, presentation layer, application layer. Okay, I remember it like that because that's how I learned it. You remember it how you want to, but you have to remember the order, especially if you want to become a CCNA or something like that. So that's the 7 layers, and we looked at the physical layer last week. And if you remember, the physical layer was all of the things you can exist in the physical world, the things you can touch, the things you can turn off and on again, the cables, the antennas, the RF signals. Oops, the wrong one. The radio frequencies. So we talked about the media. Okay. We talked about the hardware, the devices that we need to have in place, the cabling, the different types of cabling. If you remember, we talked about fiber optic cabling. We talked about Ethernet cabling. Now, come on, take a see anyone if you want one. We talked about all of those kind of things. Today, we're going to look at the next layer up, which is the data link layer, and we'll have a look at what is the significant part of this layer. Okay, let's just go in. So today we're going to look at the purpose of the data link layer, the topologies, and the data link frame. Okay, so I'll give you a couple of hints of all the important things you need to know for each layer. Okay, each layer you need to know what is the addressing information that's used. Okay, what's the addressing information? So if you remember, we talked about TCP/IP as being IP address, right? That's used at the network layer. Okay. You might have heard the term ports. Okay, so if you remember, you might have heard the term, web servers work on port 80, secure web works on 443. They're the port addresses of the services on a computer. The IP address gets you to the computer, but the port gets you to the specific service. It's like, for example, if I said, you've got a party at your house, and you want to invite me to your house for your party, so you give me your address, you write down your address, number 16, First Avenue, Kilkenny, for example, okay? So I drive my car, use the GPS, I get there, but when I knock on the door, there might be like, you might have 20 people, 5 people in your family. But Duvan invited me. So I knock on the door and then someone answers the door and I say, I'm looking for Duvan. So basically the idea of the ports is when you knock on the door of the computer and say, I want to talk to the web server. I want to talk to the DNS server. I want to talk to the Active Directory server. They all work on a different port number. So at the network layer, transport layer, it's ports. Okay? Anything above that, that's not really, we don't focus too much on. So we'll put ports, IP address. What's data link? Is there been any other type of IP address have we mentioned before? I think I said it. That's MAC address. Okay, Javon said that as well. So MAC address. Okay, that's we're going to talk about that in a second. Media access control. That's what MAC stands for. That's a MAC address. If you remember last week, we showed you how the MAC address was a hexadecimal. Okay, it uses the numbers plus the letters to give you the address. So besides knowing what is the addressing that's used at each layer, you need to know what is the protocol data unit. You're probably going, what the hell is he talking about? Protocol data unit. So obviously we send data, and at the physical layer, it's just what's it? The electronic noises, isn't it? Ones and zeros encoded into the media. So that's just electrical signals, for example. Whether media that might be. Remember we talked about amplitude modulation, frequency modulation, phase modulation for the radio frequencies. We talked about the pulses of light for fiber optics. We talked about the variation of voltage in the copper electrical impulses. So they're the stuff we're using here. So at the network layer, so we just concentrate on these bottom ones, it's called the packet. Okay, it's called a packet. You might have heard something like that. It's a TCP/IP packet. Okay, so that's what we call it at the network layer. But what's at the data link layer? Frames. Right. If you remember, so don't worry, get worried if you don't know what a frame is. That's what we call it. Okay. But what I'm trying to emphasize is that we need to know for each of these layers, data link, network, and transport really, what is the addressing information that's used, and what is the protocol data units it's called. Okay, and which devices uses it. You might have heard me talk about this last week. We have all these devices. Obviously, they're all physical because I can touch them. But I said that some devices worked at a certain layer, and other devices worked at a different other layer. Okay, so what's this device called here with all the ports? Switch. Okay, so what layer does that work at? Sorry? It's a physical layer, but data link is the highest layer it works at. Okay, so all of them are physical. I can touch them definitely. I can tell you now this is a switch with all the ports, but this device is a router. They're both physical. I can touch them. I can literally throw it at you. But no, you can't catch it. But that's why they're physical, because we can touch them. But I can tell you the switch is working at the data link layer, and the router is working at the network layer. Right. So you got to think, why are they working at why are they different layers rather than it's just the physical layer? Okay, of course they're all working down. When we say the routers at the network layer, it doesn't mean it doesn't do anything at this data link. Doesn't mean it doesn't do anything at the physical. Obviously it does. When we say it's a layer 3 device, 1, 2, 3, it's layer 3, right? It's because that's the highest layer it's working on. Okay, let's think about it. So router, you know, I've been giving you that example where if I was a router for this network, you are the network computers, this is the internet, I'm a router, I've got multiple interfaces. Inside, outside, your default gateway is this interface, this is my exit interface, and if you want to talk to someone out here, you basically tell me what you want to say, and I go pass on the message, don't I? The right people over there. Well, when you want to communicate, you're going to send a packet to the router. The router is going to look, it's like an envelope. I'm going to look at that address, IP address. Then I'm going to determine who that IP address is and where to pass on the message. Okay, so I go through my routing table, I look up where the network you want to go to is, then I pass it on to wherever it needs to go. If it's directly outside, then I can talk to the device or computer or person directly for you. Okay, so a router uses looks at the packets for the destination IP address and then makes a decision on how to forward your IP packet. That's why it's a layer 3 device, because it's making a decision at that layer. Okay, now hopefully that's not too confusing for anyone. So far, so good? Follow me? Perfect. Yeah, all right. So now that's pretty obvious. Everyone knows about IP addresses. But not many people know about MAC addresses or frames. Okay, because switches, what are switches? We just plug it in and it works. We literally can buy a switch like that, take it home, turn it on, plug it all in, the computer's in, and it literally works. We don't have to do much configuration, especially if it's a dumb switch. No configuration required at all. We don't even need to remotely manage it. We just turn it on and it'll work, and it'll do its job. Whereas a router can't. With a router, you actually have to configure it with IP addresses, with routing protocols, and turn it on to the right networks before you actually can work. So that's why you don't know much about switches. So switches looks at frames and looks at the MAC address, and what does it do? You got all of these ports, don't you? You got all of these computers, each one plugged into a different port. So if the advanced computer, this one, is plugged into port 1, and Golan's computer, this one here, is plugged into port 2. When Divan sends a communication to Divan, oh, to Golan, sorry, I'm getting myself confused. Still learning your names. It goes through his little Ethernet cables. Okay, you know what Ethernet cable is. It's the little cables at the back of your computer. Eventually comes into this port. Now this switch has to make a decision. Which port do I send it out of? Which port is Golan connected to? Port 2, right? That's what we said in our little scenario example there. But how does the switch know that Golan's computer is actually plugged into switch port 2?
Not intelligent?
Huh?
Not intelligent, maybe?
Oh, well, they are sort of intelligent. They do learn. They do learn, but how? That's what we're here to learn. We can't just say it's a black box with their intelligence and it just works. That's not what we're here for. When people who use things at home, that's what they need to know. But for people who are doing this as a profession, you need to know how. That's that. All right. So Divan said it's a MAC address table. All right. So let's go back. I know we haven't talked anything about the PowerPoint yet, but because we want to set the scene, okay? So if we have a switch, this is a symbol for a switch in Cisco. We have a table in the memory of the switch, and then we've got port 1, port 2, etc. 3, 4, 5, 6, 7, 8, 9, 10. And if we have PC1 with a MAC address ABC, we know that MAC addresses are hexadecimal, right? So it could be ABC. It's a lot longer. I'm just simplifying it. And it's plugged into port 1. Okay, so what happens? When you turn on the computer and the switch is turned on, initially it just does nothing. It just forwards it to everyone. You send me a message, I send it to out of every port. So you send me a message, and if Divan was sending a message, it was plugged into port 1, then I don't know where Golan is. I just send it out of every port. If it's on out of every port, it's definitely going to get to someone, right? So it's more like a broadcast in that situation, isn't it? But then Golan is plugged into port 2. We'll realize that, hey, that was for me. Because that's got the address in the frame was for my MAC address. Right, let's put Golem's computer here, and that's PC2, and it's CBA. Okay, not very imaginative. That's plugged into here. So once Golem gets the message, he wants to reply, doesn't he? Because obviously the communication is two-way. You ask him something, he replies with something. So when Golem sends, he'll send it into port 2 and back to Juvan. But in this case, does the switch know where Juvan is plugged into? Does the switch know where Juvan, which port Juvan is plugged into? Yeah. Yes. How does it know? Like, it just got a message from Juvan, didn't it? So what happens when we turn it on and we're waiting for the communication to happen is that once Juvan uses the switch looks at the frame, looks at the source MAC address, and maps ABC to this port in this MAC address table. But initially it doesn't know where Golem is because he hasn't communicated yet. He's just been quiet. I don't even know he's on the network. But once he replies, it will map CBA onto the second port. Then over the whole course of whatever time it takes, it maps every active port with a MAC address. So now on, after that initial part of it, instead of sending any frames out of all the different ports, you can see that's inefficient, isn't it? The switch will only send the traffic out of the port that's been mapped to your computer. You get me? So that's a lot more efficient. Instead of sending to everyone and wasting bandwidth on every port, I'm just going to send it straight to the computer that needs it. Okay? Juvan to Golem, so it goes from into port 1, out of port 2. And every other port is free. So that if Ufan and Matt are communicating on port 4 and 5, that's fine, they can communicate. At least you can communicate, and they don't interrupt each other because they're not, it's not being sent out of their ports or into their ports.
A unicast message.
Yeah, it's a unicast message, and also it's not gonna, it's like you having a private conversation in one separate room, these guys having another conversation in another room. They're not going to disrupt each other, are they? Their communication are not going to interfere with each other's communication. Okay, that's a key point. Let's get into our PowerPoint. So hopefully I've set the stage so we know that the main reason why we use MAC addresses. The main reason why we use MAC addresses for what we need to know for now. And let's keep that in mind as we're talking. Oops. All right, so the purpose of the data link layer. The data link layer is responsible for communication between end devices, end device network cards. It allows for upper level protocols. When we say upper level protocols, we're talking about all the protocols above it in the layers to access the physical layer media and to encapsulate layer-free packets and IPv4 or IPv6 into layer 2 frames. Okay, remember me talking about frames and packets? It also performs error detection and rejects a corrupt frame. So, if we're looking at this diagram, so hopefully everyone can see. All right, so this computer is going to talk to the web server. And basically, you can see that there's a layer-free IP packet, but there's also a layer 2 header. Okay, this process of actually wrapping up the packets into a layer 2 frame is called encapsulation. Okay, so if you think about it, I've got a letter. I wrote a letter, very nice message to my friend. I obviously want to send it to my friend, so I fold it up and I put it into an envelope. Okay, that's a TCP/IP packet. The envelope has the the destination IP address as in the where it wants to be sent, and at the back it's got the not at the back, but let's pretend it's a letter. At the back it's got your sender's address. Pretty normal stuff, right? But when we actually put it in the mailbox, the mailman is going to put it in the letter into his mail bag. So by putting in a mail bag, they're actually encapsulating it inside of a layer 2 frame. They don't care about the individual computer address right now, IP address that is. They care about where to take them in a local area. Okay, so this then uses the MAC address to get them to the right computer on the local area network before it can be maybe passed on to another country or another state or something like that. So that process of getting the data, putting in the packet, and then putting that packet into a frame is called encapsulation. You're putting one thing in another thing in another thing. It's like pass the parcel. You got more and more wrappings. Okay. So in the layer 3 IP packet, we have the source and destination IP addresses. In the layer 2 frame, we have the destination and source NIC, which is effectively the MAC address. Okay, let's keep on going. So we don't need to know all of this stuff, to be honest. Basically, we have the network, the data link, the local link connection sublayer or the MAC sublayer, and then we've got all of these things, whether it's an Ethernet, wireless LAN, or wireless personal area network. So that's your Bluetooth and stuff like that. And RFID, the Wi-Fi, we all know. So how much of this do we need to know? We need to know, like I said, the main things is what's it called, frame, what it used as addressing, MAC addresses, and it wraps up the upper layer protocols. If you want to do the Cisco CCNA exam, this is probably something that you do want to know. But for us in the classroom, probably not as much to pass our subject. Okay, providing access to media. Packets exchange between nodes may experience numerous data link and media transitions. What does that mean? So if Juvan is plugged into this switch, well, they're Ethernet cables, isn't it? So they use copper, okay, into the switch. But this switch, let's pretend these are fiber optic ports. Remember, to the backbone, they use a fast connection, and let's say it's fiber optic. So when it comes into port 1, it's going in as copper with Ethernet. When it comes out of this switch, because the person Juvan wants to communicate with is not plugged into this local switch, well, let's put it this way. Hey, you can make 2 switches one network by simply taking a cable. It could be fiber, it could be something else, that you plug in to 2 switches together. Like that. Okay, it's a bit like your power board. You put another power board on, you just have more power out of it, don't you? By connecting 2 switches like that, especially with these fast backbone ports like we talked about, we can connect a 24-port network for these computers into the rest of the network, which obviously literally there's hundreds of computers, thousands of computers on this campus. That's what we can do. And that's what these backbone ports are. But let's say the situation is that port, it wasn't an Ethernet port, it was a fiber optic port. So when it says media transitions, it means it transitions from copper to media, to fiber, from electrical impulses to light. So the way we do things, how we send the electrical impulses and how we send the light is totally different, isn't it? Totally different, but it doesn't matter. It doesn't matter, because as long as they're working within their own layers, it all works together. So it's just saying it transitions between different medias. Each hop along the path, a router, so this is not a layer 2 device now, this is a layer 3 device, performs 4 basic layer 2, it still works at layer 2 as well. It accepts the frame from the network, it decapsulates, so remember that TCP IP packet that's inside the envelope. It unwraps the Ethernet frame, then looks at the TCP IP packet, and then looks at the IP address, makes its routing decisions, but then when it sends it out of the other interface, it rewraps it up into a new frame with a new destination MAC address destination source MAC address and sends it out. So far, so good, guys. Making sense? Anyone? Have I lost anyone? I know this is very conceptual here. I'm trying to make it easy to understand, but let me know if it's not making sense. Okay? Topologies. There's physical topologies and logical topologies. Topologies is basically the how a network looks. Okay, how it works, how the traffic can flow. Okay, there are two types of topologies used in describing a network. There's a physical topology, literally how physically are they connected together. And there's a logical topology, which identifies the virtual connections between devices and the device interfaces and IP addressing schemes. All right, let's have a look at this. This is a simple topology. It's not simple. It's actually very complicated in the practice, but really, you've got a router. This lightning link is usually some sort of WAN link. In this case, probably serial. It's going to this cloud, which represents a network you don't necessarily control, so like the internet, and it's going to another router. But it's only one point on this side and one point on this side. This is what's called a point-to-point network. Okay. So there's sorry.
Is the port of a serial table?
Yeah. So you asked me what the serial cable port looks like. That's a serial port. And later on, you definitely will do this, but let me show you on this side. This is an example of a serial cable, okay, as opposed to an Ethernet cable. This is a small form factor serial cable, and basically you find a router with a serial port, and now we've got a point-to-point link between this router and this router with a serial cable. That's effectively what this is saying. All right. So that's what we'll do in the future. Definitely, this is part of your practical test. That will be part of the subject. You'll be needing to do that. Okay. But let's keep going. But there's other topologies. There's a star topology. That's like when we have a switch in the middle, right? And we have all these computers plugged into a switch. It's like a star, isn't it? We can have this extended star. Remember how I just linked two switches together? So this could be a switch here, this could be a switch there, then I linked the two switches together, and that's an extended star topology, and that's what most networks are these days in real life. The older style networks include the bus network. I'm not sure if anyone has experienced this. Literally, have you seen the TV antenna aerial plugs? They're like they're called coaxial. All right, we don't have any in this room, but in some of the older classrooms, we still have the things running around the room, literally from one end to the other end, like that. It's called a bus topology, and you notice that there's these things. It has to be terminated at each end. And if you take one computer off, unplugged, and you don't terminate that plug, then the whole thing doesn't work. The whole network doesn't work. It was it was a nightmare to troubleshoot, especially with students. They unplug one and then the whole network goes down, doesn't it? Okay, so then there's the token ring or ring topology. So instead of being plugged into one device at the front, in the middle, they're plugged into a ring. And if it's a token-based ring, it means only the computer with the token can talk. It's a bit like if you go to a meeting and only the person who's recognized as having the floor can talk, the person with that token can talk. Then half duplex versus full duplex. So duplex, what does it mean? Can I talk and listen at the same time? I'm not that smart, probably not. As they say, I'm a man as well, so I probably can't. But computers can. Okay, if they have everything at the same time, you can send data and receive data at the same time. That's called full duplex. Half duplex is where you're either talking or you're listening. And unfortunately, our class communication is a bit like that. I'm talking, so you're listening. We're working only half duplex. It's only half as fast. Just imagine I can talk and listen at the same time. I can increase double the speed, couldn't I? Right? So half duplex, as the name suggests, is half the speed of the full duplex. Half duplex communication allows one device to send or receive at a time on a shared medium. What's a shared medium? A shared medium is where the thing that we're communicating through is shared by everyone. Like now, the air in the room is how I'm communicating to you guys. If you start talking, you're going to cause noise in the same medium as I'm trying to communicate with, right? So therefore, your noise, if you're having a chat back there, your noise might mean that what I'm saying is not able to be heard by someone else. So when you have a shared medium, it means everyone can affect everyone else's communication. There's what we call collisions. Okay, collisions. It's like when you have lots of cars on the same road. The road is a shared medium. If they don't drive properly, you can have an accident, and that's a collision, right? What happens there? That no one can communicate for a while until they clear up the collision, and then they start again. All right, so example of half duplex networks include legacy Ethernet buses, like I showed you just before, but also the Wi-Fi network. Wi-Fi is using radio frequencies, isn't it? Through the air again. So if it's the same air, okay, then they're going to be sharing that medium. Full duplex communication allows both devices to simultaneously transmit and receive on a shared medium. Ethernet switches work at full duplex. So remember how I said the ports they're plugged into? Which way? This way. The ports they're plugged into, they're full duplex. They can be full duplex because the switches using a MAC address table can send only to the computers that need to receive it. Okay. Whereas the old-fashioned hubs, you've heard of hubs before? Maybe they look like switches. They look like switches, but let's have a quick look at. Okay, so Ethernet hub. Okay, let's have a look. So this is a Ethernet hub, for example. It looks like a switch, doesn't it? Basically, it does the same role as a switch. But the problem with this hub is this is a layer 1 device. Okay, layer 1 device because it's only physical layer. It's only for connectivity. It does not do anything with the layer 2. Remember, layer 2 was the MAC addresses and frames. Remember how a switch uses the MAC address to build a MAC address table and then work out which ports need to be involved in the communication. The hub just doesn't care. It just sends it out. Okay, it just sends it out all the ports all the time. It's simple, isn't it? But it means it's only going to work at half duplex, and in this case, it's a 10 base T, which is 10 megabits per second, which is very slow. You don't need me to say that to you. So there's contention-based access. What's contention-based? Contention is when you're fighting for something. Competition. So when you're driving on the highway, you're sort of fighting with every car to get the space on the road, aren't you? If there's a space opens up, you want to take it to go faster. You're fighting with every other car that wants to take that space, don't you? So who gets it? Well, depends. Whoever gets there first, possibly, or maybe you could have an accident because you're both going for it. So contention-based access is all nodes operating in half duplex, competing for the use of the medium. Examples are the carrier sense multiple access collision detect used on the legacy bus technology. So what does that mean? Carrier sense multiple access collision detect. So let's pretend we're all computers and the air is our traffic, our shared medium. Okay, so Javon, how was your day today? What are you talking about? What did you say? Say something? What do you mean? See, you see how when he's talking, I'm talking, no one can talk? So that's what the collision is all talking about. So in that, have you ever had that situation where you're about to talk to someone, but you keep on talking at the same time? What do? You sort of just back off, don't you? You back off, you stop, you pause, and then you start again. But hopefully you're not starting at the same time, right? So that's what carrier sense multiple access collision detect is all about. Okay, so So the carrier sense, I sense the carrier, the media. Multiple access, multiple computers accessing at the same time. When the collision detect, remember how we were just having that little demonstration where we're both talking at the same time? We can both sense that, can't we? We can both detect that we're trying to talk at the same time, so we stop. So the computers, that's what they're doing. They detect a collision where two packets or two frames are sort of having an accident or having collision. Then what happens is they have a back off timer. It's random. So they back off, stop talking, let the collision clear, and then they start talking at a random time. Hopefully that random time is different to someone else, another computer. All right, there's another type as well. It's called carrier sense multiple access collision avoidance. Well, it's a lot easier to not have collisions than to have collisions, then everyone can't talk, right? So avoidance, as the name suggests, is used for wireless LANs. Remember, wireless uses the same media. So it's sort of, the wireless cards are sort of sensing, is anyone else communicating? If they're not, I'll communicate. Then there's controlled access type networks. Okay, so deterministic access when each node has its own time on the medium. These are not so much used now. They're used in the olden days. Remember I talked about a token ring? Okay, that means this is the talking stick. If I've got it, I can talk. Now, he's got it, so he's got it. He can talk. I shouldn't be really talking now. But so basically on this token ring network, what's your name? Yeah, actually take a seat, join in where you can. Okay, so basically anyone with this token can talk. That solves a lot of problems, right? There's no talking over each other now, and only the person with this can talk. And that's what's called a token ring network. But no one uses that anymore, because you can now tell that out of 20 computers, only one computer can talk. That means 19 computers are waiting around doing nothing. So that's very slow, isn't it? All right, so CSMA-CD, carrier sense multiple access collision detect, is used by legacy LANs where they're working only in half duplex. That's where you have the hubs that we talked about. It uses collision detection process to govern when a device can send and what happens if multiple devices send at the same time. So device transmitted simultaneously will result in a signal collision on the shared media. The devices detect this collision and then waits a random period of time before it starts again. Okay, like I said when we were having that conversation. Collision avoidance is used by the IEEE 802.11. So you might have heard the 802.11 standard here and there. You might have go 802.11, 802.11n, 802.11 AC, AX. You might have heard of those different standards. They're different Wi-Fi standards. They operate at half duplex mode where only one device sends and receives at any one time. So that's why Wi-Fi is a bit slow as well. And it uses collision avoidance, which is a process when the device can send what happens if multiple devices send at the same time. So when transmitting, the device also includes a time duration needed for the transmission. So basically it's this. Hey guys, I'm going to talk for 2 minutes, and then someone else can talk. So everyone just waits for me to finish my 2 minutes, and then they start talking. Other devices on the shared medium receives this time duration information and knows how long to keep quiet. Okay? Data link frames. Remember how I said the frame is the important thing that we need to know? Data is encapsulated, wrapped up in a data link frame with a header and a trailer. If you think about it, think of a semi-trailer, big truck. Okay? The cargo is the payload. The cargo is your data. Okay, if you want to send a truck from Adelaide to Melbourne, you have to put on a truck. It's got a big head at the front. It's got a trailer. It's got some lights at the back. It's got headlights at the front and number plate at the front and the engine at the front. And it's got on the back. It's got a trailer. It's got some brake lights, reversing lights, all those kind of things, and number plate at the back. So if you like to think of it, what a frame has is a header, the big semi-trailer head. Then we've got the data, which is the payload in the middle, and then we've got the end of the trailer with the warning lights and all that kind of stuff. These things are all there for a reason. Their reason is that they need to use the header to tell the system where it's going, and it needs the trailer to say I'm finished. Okay? So the amount of control information carried within the frame varies according to the process and the topology. So if we look at this, so this is the header. Well, if you remember, we got the TCP/IP packet from the layer 4 or 3. That's actually being encapsulated, so that's why it's called a packet here. Okay. Then we've got the trailer. So what's in the header? It's a frame start to say this is the start of a new frame. Don't get confused with any other frames that might have been sent. So it's just telling how it's all ones and zeros, and in the stream. So how does it know? Well, this thing says it's a new one. The addressing, the source and destination MAC addresses, the type, as in the type of layer 3 protocol that it's carrying. The control identifies the flow control service. Like, for example, flow control is how fast can your car drive down this highway? Okay, if it says 100 kilometers an hour and there's another car doing 200 k's an hour, that's obviously going to cause some problems, right? Because the car, the road's not meant to handle that fast, or the receiver can't handle that much data at the same time. And then at the trailer, we've got error detection and frame stop. Frame stop meaning this is the end of this frame. Error detection meaning that once you get all of this, if you do this computation, you should end up with this value. And then if you receive this and you do the same computation, and if you receive the same value, you know that the data hasn't been corrupted. But if you get a different value, maybe it's been corrupted, and you should ignore it and ask for retransmit. Layer 2 addresses are referred to as physical addresses. They're contained in the frame header, and they're used for local delivery. That's a key term here, local delivery. MAC addresses are only used on the LAN. They do not cross between one network to another network. You can never use a MAC address to find a computer that's on the internet, for example. They're only used in a local area network to find the individual computers. Once you cross a router, that frame, the MAC address is taken off, a new MAC address is put on there. Okay, you can see that here in this picture. You got the layer 2 and layer 3 packet. The layer 2 frame is encapsulating the layer 3 packet. When you send it, it goes to the router because it's going to another network. The router receives this. It looks at the layer 2. So yes, it was meant for me. Then it decapsulates, takes it out, and looks at the layer 3. On the layer 3, it works out where's the destination network with its routing table. Then it resends it. But in this case, the layer 3 is exactly the same color because that doesn't change. But the layer 2 is different color because it has changed. It re-encapsulates it with the source MAC address here and the destination MAC address of this. You see how the MAC address is a different color every different network. So each interface of a router is a different network. So each time it crosses a router, it gets decapsulated, opened up, and a new frame is created when it gets sent on with new source MAC and new destination MAC address. Follow me? Anyone finding it hard to understand? I know it's a lot. Okay, so let me know. So LAN and WAN frames. So for our purposes in this subject, all you need to know about is Ethernet, wireless, and that's it. Okay? Point-to-point, high-level data link control frame relay is not something we need to know much in this subject. Definitely when you go do the yeah, the future levels of Cisco in the diploma, you'll definitely do more of this stuff. But what do we need to know? Well, not that. Just the Ethernet and the wireless, really. Okay. So that is the end of the PowerPoint for the first session. And hopefully I haven't put anyone to sleep or lost you guys. It's a little bit dry, this subject, when you're talking about these layers and stuff like that. But conceptually, it's very conceptual. But really, like I said, when I did the diagram and the examples, it's actually used. It's actually used for these devices to work properly. All right, so I'll give you an example. If I was a hacker and I knew you had a switch that had a MAC address table, what does that mean? If I want to, the only computers, if I just sit there quietly on my port, the only traffic I would be able to sniff or see is the traffic that's coming to my port, isn't it? So remember, if I'm plugged into this port here, based on the MAC address table, the switch is not going to send anyone else's data into that port, except for the one that's meant for my computer, right? So if I'm an attacker, and I am on a network which has a switch, and I'm trying to listen in on everyone's conversation, I can't. Because I won't be getting anyone else's conversation besides the one that's meant for my computer. But if I was on an old-fashioned hub network, I could just sit there and just listen to everyone's conversation because I'm in the shared medium. If you feel like this room, or I can, if I listen carefully, maybe Kaylin and Basid back there is having a conversation, I'll probably hear what they're saying. Maybe I can pick up some secrets. Okay? But knowing there's a MAC address table, what if I did something? What if, as an attacker, I fill the MAC address table with useless bits of information? Remember how we talked about the buffer overrun sort of attack on Monday? Were you there? No, you weren't there. You don't know that class. So basically, when you create a program, there's variables designed to store some information. Okay, what if I, as an attacker, put more information into it than it's meant to handle? And there's no error checking because it just lets me do that. Well, if I can do that to the MAC address table, if I stuff it full of information that's useless, it becomes the MAC address table becomes so useless that it reverts back to the original state. Remember that original state where if you said something, it goes out of every port, isn't it? Or if I was a hacker and I can make that switch go into that node, now I can sit back and just listen to everyone's conversation again, can't I? So that actually used to be an attack. Okay, that used to be an attack, and how some of these people used to sniff out information is to force a switch into that mode and then listen to your secure communications. And if you weren't using a encrypted communication like HTTPS or something else that's encrypted, then I can just use something like Wireshark. Have you guys used Wireshark in the subject yet? No? But once you do, I think you're going to use it in this session. Once you use Wireshark, you can actually pick up the frames, pick up the packets, and open them up and read them. And if part of your conversation is hi telnet server, my username is admin and my password is password1, and if it's using telnet, it's clear text, I can just pick out exactly the username and password out of that. So that's what's used to happen. Okay, obviously that if I'm talking about it, they fixed it. Okay, so don't go try doing that. So they fixed that kind of error, but I'm just trying to emphasize the fact that we need to understand how it works so we can understand the possibilities of how someone could use this against us or how we can control the network. Okay, so what we need to do in this session is, I think, if we, where are we? Okay, so we're up to the not Ethernet switching, is the data link layer, isn't it? So I think in this one there's not much activity except for a quiz, but obviously use this time. So we've got about an hour left of this lesson to catch up on any labs you might previously have had, or start working on the first 9 questions of your assignment 1. If you remember, we talked about it last week, and hopefully we made it understandable for everyone. But the next lesson, we will definitely be doing some more lab work. And remember how I said Wireshark? There's Wireshark, a lab for Wireshark.
Are we allowed to install Wireshark?
Sorry?
Are we allowed to use Wireshark here?
Yeah. That's why it's installed on your computer right here. And we can actually capture refresh interfaces. Let's go to options. Which interface do I want to capture? Which one am I connected to? Ethernet is enabled, and I can actually now capture. Okay, let's stop it. Okay, I've just done a really quick capture, but I can see that there's all these communications. So the way you read it is, look at all those communications. Okay, that's all happening in the background. But there's one that I can recognize that's using no, that's using HTTP 1.1. Let's see if there's any people. Let's do something again. We'll start it again, and we'll start a command prompt, and we'll do a NS lookup or www.google.com, and obviously we did an NS lookup there. Let's stop it, and let's see if we can find a UDP port 53. So it's in here somewhere. Yeah, the thing is that there's so much communication between. This is my computer, hopefully that's what it means, and this is the destination computer. I'm going to try to find this specific communication. But okay, I'm not necessarily finding it, but let's just click on any one of these. Let's take this one, for example. If we open this up, we could actually look at the frame information. We've got our, if we expand the Ethernet, we can see that, hey, remember how we talked about the headers? So this is the frame information, the Ethernet header. We've got the destination MAC address. We've got the source MAC address. We've got the type of layer 3 protocol we're using, which is IPv4. And then if we go to the IP, so with Wireshark, we can now look at the IP packet as well. We can look at the header. We can look at it's a user datagram. Remember we said that there's a source port and a destination port. Remember we talked about how the destination port is like me going to your house and knocking on the door and asking for you or the service. In this case, it's 1900. I don't even know what that port is meant for. But then we can look at the data, and it's telling me it's a data hypertext 1.1, which is a protocol version. And then the request is this. It's a Microsoft Edge is making the request, and it's going to this. It's going to this computer. It's basically my computer talking to Microsoft, I believe. So this is Wireshark. This is a tool that you're using as part of your labs to learn about these things. But quite simply, I can take this Wireshark and look at the data that's in there. If we look at this part, for example, I can see it's giving me actual information.